Hello and welcome to week 6, lecture 1. We're going to be talking about rotational kinematics. So we're covering chapter 7-3 and then 8-1 and 8-2. We're going to do sample problem 7-2 on the center of mass of a many particle system. And then we will talk about the variables of rotational motion. For the sample problem, we have a system of 3 masses. Each mass is experiencing a different net external force. The location of the masses and the direction of the forces are shown in this figure. So yeah, let's work on this problem. Okay, so our 3 particles. Let's write down what we know. So mass 1 equals 4.1 kilograms. Mass 2 is 8.2 kilograms, and mass 3 is also 4.1 kilograms. And then our net external forces, so force 1 is 6 newtons in the negative I hat direction, which we can see from the diagram. F2 is 12 newtons at this 45-degree angle. And then F3 is 14 newtons in the positive I hat direction, which again, we can see right there. So the first thing we want to do, well, it also asks for it, asks us where the center of the mass of the system is and what the acceleration of it is. So first thing we want to do is find the center of mass. And we have, this is an x-y coordinate axis, so we have equations for finding the center of mass, the x and y positions of the center of mass. So for the x, it's 1 over the total mass of the system times the sum of the mass of each mass and its x position. And then the same thing is actually true for y. It's just y instead of x. So let's take a look at what we have here and get the x and y values for each one. So I'm going to call this r, but we'll have x and y. Let's see. So mass 1 is at negative 2x and 3y. And these are in centimeters. For 2, we have, see, 4x and 2 and y. And then for the third one, we have 1 in x and negative 2 in y. Okay, so we can use those to find the x and y positions of the center of mass. Maybe I'll put centimeters here for all of them so we keep track of our units. So let's find the x coordinate of the center of mass. Actually first, sorry, let's find the total mass, which is again just the sum of all the masses. So it is 4.1 kilograms plus 8.2 kilograms plus 4.1 kilograms. And that gives us 16.4 kilograms as the total mass of the system. Now let's find the x coordinate of the center of mass. So again, it's just 1 over m, the sum of the mass times its position in x. So we have 1 over 16.4 kilograms. And then just gonna parentheses there. Let's see. First one is 4.1 kilograms times negative 2 centimeters plus 8.2 kilograms times 4 centimeters plus 4.1 kilograms times 1 centimeter. Okay, so we get the x coordinate is 1.75 centimeters. So that's the x coordinate of the center of mass. And then let's do the y, the center of mass. 1 over 16.4 kilograms, 4.1 kilograms times 3 centimeters plus 8.2 kilograms times 2 centimeters plus 4.1 kilograms times negative 2 centimeters. And this is 1.25 centimeters for the y component. Okay, so then we have our position of the center of mass as 1.75 centimeters and 1.25 centimeters. Okay, cool. So we answered the first part of the question. Check, yay. Now, though, we want to know the acceleration. And the thing we covered last week with this is that if we can treat the center of mass, we can treat a mini particle system and external forces acting on it as if the external forces are only acting on the center of mass, and also as if the mass is all concentrated at the center. So we know our position of the center of mass. So now, oh, I'm out of room. Okay, out of page. So now let's draw a free body diagram. So this coordinate axis here is not going to match the one that we have on this page, because the center of mass is right there and the origin is here. So just heads up. But let's draw those forces. So we have F1 in the negative x direction, F3 in the positive x direction, and then we have F2 at a 45-degree angle up here, 45 degrees, and this is F2. And so this means we have a y component of 2 and an x component of 2, not necessarily that big. So this is, we just then do our sum of forces equations. Well, actually, first, I guess I will say that the y component of 2 is going to be sine of 45. And then the x component is going to be cosine. Okay, now sum of forces in the y direction. So again, remember, this is the total mass of the system times the acceleration of the center of mass. So that's the acceleration in the y direction for this part. And the forces there's only one force in the y direction, and it's just the y component of the second force, 2y, or F2 sine of 45 degrees. And then sum of forces in the x direction. Again, this is capital M, meaning all the masses, times the x component of the force. And then we have several forces in the x direction. So we have force 3, and then we have the x component of force 2. Both of those are in the positive x direction. And then we have F1 in the negative x direction. Cool. So we should, well, I guess we can just take a look. I think, though, we know everything we need. We know this. We want both of these. We know what F2 is, and then we have the angle. Same with that one, and then we know, yeah, the magnitude of all the forces. So cool, we can just plug in our numbers. So let's, I guess, start with A. Start with a Y. Of course it's A. So I'm just going to divide the total mass on both sides. So I'm solving for the acceleration in A. So for this one, 1 over m equals F2 sine of 45. And that is 1 over 16.4 kilograms times 12 newtons sine of 45. And this is 0.52 meters per second squared. So that's the y component of the acceleration. And then the x component, also 1 over m, but there's more stuff. We have f3 plus, and then I'm going to plug in this equation for the x component of f2, cosine of 45 minus f1. So let's plug in those numbers. 1 over 16.4 kilograms. F3 is, I can't remember, 14 newtons plus 12 newtons cosine of 45 degrees minus 6 newtons. And this is 1.01 meters per second squared. So we can write our acceleration. Oh, I should put subscript center of mass. Acceleration of the center of mass like this. 1.01 meters per second squared in x and 0.52 meters per second squared in y. And technically we could leave it at that. I think they actually want like the angle and the vector form, or like the magnitude value, the total magnitude value of the acceleration. So that means we want to do the acceleration is the square root of the x component squared plus the y component squared. Square root of 1.01 meters per second squared plus, oh, sorry, that's right. The whole thing squared. Plus 0.52 meters per second squared, whole thing squared. Square root of that. So we get 1.1. Okay, but then we need to know what angle that is at. And looking at our free body diagram, I think we can comfortably say that our acceleration, our net force and acceleration are going to be in this quadrant here, the positive x, positive y quadrant. So let's just really quickly look at that. So we can say, I mean, I don't know what the angle is, so I'm just making that part up right now, but just so we can tell which way we should orient the tangent. So it looks like, I think generally it's a good idea to take your angle to be from the positive x-axis, because that's kind of standard. So that's what we'll do, and tangent is opposite over adjacent. Opposite is y, and adjacent is x. So let's plug in our numbers, and we have 0.52 meters per second squared divided by 1.01 meters per second squared, and we get 27 degrees. So the acceleration of the center of mass is 1.1 meters per second squared at 27 degrees counterclockwise from the positive x-axis. Hey, cool. So I wanted to cover that before jumping into kind of a new topic, because I didn't get to do an example problem with you for you on this topic before. So back to the slides now. Okay, so we're talking about rotational motion, and specifically we're going to define the rotational variables. So we have a situation of a 3D object rotating in the XY plane. That's what this is. This is kind of our 3-dimensional object. And it's at a height along the z-axis, but it's only rotating in x and y. It's not moving like up and down. So we can also just think of that as motion within this xy plane. And we have phi here to represent the angular position of the object. And so that's just like the angle it's covered from the positive x-axis. So now though, let's look at 2 different positions of our object. So actually really quick, right now we're ignoring the shaded area representing like the physical form, and we're just thinking of this kind of radial line representing our object now. So that's what these are. These technically are the object. We just be too much on your screen to have the actual physical form there. Anyway, so we have two different positions of our object at time 1 and at time 2. And individually, the positions are given by the angles phi1 for time 1 and phi2 for time 2. And the angular displacement is the difference between those two angles. So phi2 minus phi1 gives us this angular displacement also here. And we can get the average angular velocity by dividing the angular displacement by the time interval. So average angular velocity is given by omega, W, but it's a Greek W. And so it's just the angular displacement divided by the time interval, or phi2 minus phi1 over time 2 minus time 1. But if we want the instantaneous angular velocity, we need to decrease the interval until we're pretty much just taking the derivative of the angular position with respect to time, and that's how we get the instantaneous angular velocity. The angular velocity is given, like I said, by omega. In rotational motion, counterclockwise motion is positive. And so this is just like how, generally speaking, motion to the right is positive in linear motion. But since this is rotational motion, we have to think clockwise or counterclockwise. And so counterclockwise motion is positive, just like motion to the right is. And clockwise motion is negative, just like motion to the left is. And another important thing to note is that all points on a rigid body have the same angular velocity. So any place along this line has the same angular velocity. And the units of angular velocity are either radians per second or revolutions per second. And we kind of talked about going from radians to revolutions like earlier in the quarter. But what you just want to think about is one revolution is just like one time around a circle, and that angular displacement is 2 pi radians. So to go from radians to revolutions is just 2 pi. Okay, and just like what we did with average angular velocity, we can get average angular acceleration by dividing the change in angular velocity by the time interval. And for instantaneous angular acceleration, we need to decrease the interval until we're just taking the derivative of the angular velocity with respect to time. And angular acceleration is given by alpha. So just like for angular velocity, counterclockwise acceleration is positive and clockwise acceleration is negative. And this also works just like linear acceleration, where if the rotation is slowing down, then the angular acceleration is in the opposite direction as the angular velocity. And if the rotation is speeding up, the angular velocity and acceleration are in the same direction. And just like the angular velocity, the angular acceleration is the same for all points along the object. And then the units are radians per second squared or revolutions per second squared. Oh, and that is everything for this lecture. And we will be spending more time with this rotational motion stuff coming up.